Guys, welcome to the part 4 of conduction, and here we are going to talk about critical thickness of insulation. Piping insulation is a very common practice in chemical plants. So the question is why we need insulation, and there are three main objectives of installing piping insulation. So first is for energy conservation. So we know in chemical plants we have pipes. We have piping system delivering hot fluids from one unit operation to another. So this piping carrying the hot fluid, the energy, the heat will lost to the surrounding if there is no insulation, and all this heat when lost to the surrounding, causing the temperature of the hot fluid reduce, and extra cost is needed in order to reheat this so-called colder process fluid. So installing piping insulation helps to conserve energy. And the second reason is for safety. So we know that workers are exposed to they have opportunity, they have high chance contacting with the piping surface. So if this piping surface with very high temperature, okay, are not insulated, then the workers will get hurt, okay, from contacting with the hot surface. Okay, so according to one article I read online, so any piping carrying hot fluids above 65 degrees Celsius, piping insulation is needed for protection purpose. Then the third reason is to prevent moisture formation and accumulation on the surface of the piping system. Of course, this is applicable not for hot fluid piping, but for opposite is for cold fluid piping, meaning the pipe carries cold fluid. Okay, so this cold fluid, since the temperature is colder, then it causes the moisture to condense on the piping surface, and all this moisture that condensed will cause different problems. For example, rusting, corrosion, okay, and maybe the growth of microbe, the growth of different types of molds. Okay, so maybe if there are too much water, then it will drip onto the ground, then it will also become a hazard to the workers, causing slippery flow. Okay, so these are the three reasons for installing piping insulation. You can see from the picture examples of insulated pipes. Okay, this is the pipe, and here you see it is covered by a layer of insulating materials. Okay, so same goes to this copper tube. So it is covered by a layer of insulating material, and normally this insulating material, they are insulators, okay, meaning they have very low thermal conductivity. Okay, so besides choosing the right materials, another question we have is how thick the insulation should be. Okay, because if it is too thick, first we will have the issue of higher cost, okay, meaning more money need to be spent. Another issue would be the piping system will become more bulky, take out more space. Okay, so this is not something we want it to happen in the industry. Okay, because we want to save cost, we also want to save space. So that's why we give you we share with you this idea of critical thickness of insulation. Okay, it's important to have this basic idea, okay, so that in designing piping insulation, so we know what are the important factors to be taken into consideration. And another reason why understanding about this critical thickness of insulation is important is if if insulation is installed improperly, so or without proper understanding uh, about this critical thickness of insulation, you might end up, let's say in your case A, okay, you want to install insulation because you want to prevent, you want to, cannot say prevent, you want to reduce the heat losing, okay, heat loss to the surrounding, okay. But do you know, if you don't understand about this concept, to critical thickness of insulation, you might end up, after installing the insulation material, okay, you end up losing even more heat to the surrounding as compared to without insulation. Now you might have one question in your mind: how come? Is that possible? Okay, so that's why I want you to focus on the following slides on the explanation. Okay, now let's have a look on the cross section of a pipe carrying a hot fluid. Okay, this hot fluid is heating up the pipe, so making the temperature on the pipe outer wall, okay, outer surface, to be at T1, okay, and the outer radius of the pipe is R1. So we know that we should have one inner wall, right? You should have one inner wall, okay. So, and this is the thickness of the pipe wall, okay. But that is not our concern. But I just want to show you this is the actual situation. Okay, there is an inner wall, and this is the pipe wall, okay, with certain thickness, okay, and this hot fluid is heating up the pipe wall, so making it making the outer surface to be at the temperature of T1, okay, and this T1 is higher as compared to the surrounding temperature, okay, which is at T0. Okay, T1 is bigger than T0, so we know that heat will be transferred from the pipe wall to the surrounding, okay, and the surrounding has a convective heat transfer coefficient of H0, okay. So, and we add one layer of insulation on the pipe surface, okay. So after adding this insulation, so making the radius to be R2, okay. So this is the scenario, okay. And by referring to this, now I want you to pause for 10 seconds and think, okay, how many resistances to be overcome if the heat were to be transferred from here, the outer wall of the pipe, to the surrounding. Okay, pause for 10 seconds now. Okay, and you are right if your answer is 2. Okay, there are 2 resistances. The first resistance is R1 caused by conduction. Okay, conduction due to the insulation material. Then the second resistance is R2 caused by the convection, okay, caused by the air, surrounding air. Okay, so this is convection, and R1 is due to conduction. Okay, and now I want you to pause for another half a minute and come up with an equation, okay, of heat transfer rate Q. Heat transfer rate Q equals to what for this system? Okay, remember I give you a clue. Q is delta T over Rj, right? Total resistances. So how many resistances are there? 2. Then what are the resistances? Okay, it's R1 plus R2. So what are the R1? What is R2? Okay, pause for 30 seconds and try to figure this out. Okay, and now let's check your answer. Okay, so this should be what you obtain. Okay, so this is the answer, and you can see the first part is R1. Okay, so because it's a cylindrical system, so this is R for cylindrical system, you have learned it. And this part is R2, actually is 1 over A H, and we know A for this cylinder is actually 2 pi R L. So that is why we get this answer. Okay, now I want you to have a look on this equation. Okay, Q means how much heat is lost. Okay, how much heat is lost to the surrounding, okay, per unit time. Okay, this is Q. So from the equation you will see, okay, when R2, meaning when the thickness of the insulation increase, then this part R1, when R2 increase, you will see resistance for R1, meaning resistance for conduction increase. But it's the opposite for the R2. When R2 increase, you will see resistance, okay, R2 resistance for convection decrease. Okay, so what does it mean? It means when you increase the thickness of insulation, what will happen is less heat, okay, less heat will be lost through conduction. Okay, but opposite happen. When you increase the thickness of insulation, more heat will be lost through convection. Okay, so now meaning we have two competing factors. Okay, when we increase the thickness of the insulation, so less heat will be lost through conduction, but more heat will be lost through convection. Okay, so what does this tell us? It means, okay, there will be R value, a R2 value, okay, a R2 value, or on other words is there will be a thickness, insulation thickness, where you will have the maximum heat loss. Okay, you will have the maximum heat loss. So the question is how we can determine this R2. Okay, how we can determine this value of R2 where it leads to maximum heat loss. Okay, the answer is, you learned it already in calculus, because we know when we differentiate Q, dQ over, when we differentiate Q over R, okay, so we will get, okay, we'll get this. Okay, you can try yourself. Okay, we'll get this, and this dQ over dR, when dq over dr equals to 0, so we will be able to get the R2 where the maximum heat loss is obtained. Okay, let me explain using this graph. Okay, so this is the equation for the system. Okay, and this is the graph. Okay, this curve represent this equation. Okay, so you see these two competing factor when R2 increase. Okay, when R2, you see when R2 increase, when R increase, then what will happen is first the heat transfer rate, meaning heat loss, will increase until it reaches a maximum. Okay, then it decreases when you further increasing the insulation thickness. Okay, so how to get the how to get the R2 which will give us the maximum heat loss. Okay, how? So it's here. So how we can get it? So I explained already just now. If we differentiate this with R, then when this becomes 0, so it will give us this point, right? Because you learn in calculus, so that is the where the maximum point is. When dq over dr equals to 0, then is where you have the maximum value. Okay, because dq over dr is actually the slope of this curve. So when the slope equals to 0, it means is we either at maximum or minimum point. Okay, so here this is where you can get your our maximum heat loss, the R which leads to maximum heat loss, that is using dq over dr and equals to 0. Okay, here let us continue. Yeah, so dq over dr equals to 0, so this is what we get. So let's see one by one. Term number 1, term number 2, and term number 3. Okay, when this equals to 0, so we know that term number 1 not possible to be 0 because temperature cannot be 0. Okay, so this part cannot be 0. Then this part also cannot be 0 because if this part becomes 0, then the whole term will be infinity. So the only possibility is only term number 3 can be 0, because when term 3 equals to 0, then when times 0, then the whole terms can be 0. Okay, then it leads us to here. So this term becomes 0, then we continue further. At the end we will get R2 equals to K over H naught. Okay, and this R2 is actually the RC. What is RC? Okay, is critical radius. Okay, or we also call it critical thickness. Okay, this is the thickness, this is the R, which will give us the maximum heat loss. This graph, then from this graph is very clear. Okay, so this is the RC, the critical thickness of insulation. So why this is important? Because, so still remember during the introduction I mentioned, if insulation not properly designed, or if it is designed without the understanding about critical thickness, you will end up you want to install insulation, the purpose is to reduce heat loss, but you will end up increase heat loss. You will lose more heat if you don't understand this concept. So you see, let's say So this point here, you have the pipe is without insulation, but once you install insulation, okay, let's say it's 1 mm the thickness, okay, you end up initially your heat loss is here 0. Let's say 38, okay, watt. Okay, but after, let's say you don't understand, okay, you install the thickness is 1 mm, okay, to save cost. So what will happen is you end up actually you lose more heat as compared to without insulation. Okay, so even let's say you say I install, okay, the thickness is 5 mm, let's say, okay, but what will happen is as compared to without insulation, you will still lose more heat after installing the insulation. Okay, so it forfeits the purpose. So that's why it's important, okay, if you want to install, the purpose of installing insulation is to reduce heat loss. You must ensure after installing the heat loss is, I think, should be beyond this graph. Okay, you want to ensure the heat loss is lower than without insulation. Okay, so this is very, very important. Okay, okay, and another thing I want to make clear here is, so these values, this value actually will be different when the value of your K, value of your H changes. Okay, so K depends on the material of the insulating material. H depends on the environment. Okay, so this is just an example, so don't take this graph as a standard, yeah, but I would say the shape is like this. Okay, so but the value of RC we learned previously equals to K over H. Okay, so in terms of application, so let's see, of course, for us chemical engineers, I think the main application is piping. So for piping, if the purpose is for if the purpose of installing insulation is for reducing heat loss, then this is one thing we need to ensure. We must ensure the thickness is thick enough. The thickness of the insulation is thick enough until the heat loss, the Q, is lower than without insulation. This one we must bear in mind. But there is another application for insulation, that is for wires. Okay, for wires, we know for when the current flows, so it generates heat. Okay, so wire, so and this heat is not good for the wiring system. So we want to actually release this heat to the surrounding. Okay, so that's why you see we want to maximize the heat loss to the surrounding for wiring, for electrical wire. Okay, so that's why you see insulating material for electrical wire are normally very thin. Okay, very thin, because when you have thinner insulating material, then you lost more heat. Okay, if possible, maybe here at the RC. Okay, but for a piping system for reducing heat loss, then we must ensure after the thickness should be enough to ensure that the Q is lower than without insulation. Otherwise, it forfeits the purpose. Okay, and finally, in order to enhance your understanding, we design this activity, okay, for you to try in group. Okay, so read through it and try to solve this problem. It's like a real life industrial problem. Okay, so what does it mean by schedule 40? Okay, you can check your textbooks. I think on the only version 3 has the what do you call that, the appendix. Okay, go and check the appendix in your textbook, you will know what does it mean schedule 40. Then from there you'll be able to know what is the outer diameter, okay, of your steel pipe. Okay, then okay, some of the information you need to search in internet. Okay, so this is to tell you that in real life, when you work in industry, all this information will not be given to you, but you need to search either online or go to library. Okay, so you need to identify suitable material. What are the material? You go and search. Okay, go and do some search online. Okay, Google, then and you look for suitable material for insulation. Okay, then you get the information for the K. Okay, you can choose, most importantly, you need to justify why you choose that material. Okay, then from there you calculate the RC. Okay, then okay, then H is also not given to you, so we want you to search online. Okay, under, let's say, a normal windy, not so windy environment, what is the typical H value? Okay, go and search online, then propose a suitable thickness for insulation. Okay, so that the the purpose of installing the insulation can be achieved. What are the purposes? The purpose is for energy conservation and also for safety. Okay, yep, that's all. Enjoy your learning.